In this video, we will dive into the engine room of quantum electrodynamics, or QED. This is the name of the quantum field theory which describes the electromagnetic force at a fundamental level. We will thus use Feynman diagrams to discuss some of the most key processes like the electromagnetic attraction and repulsion, which we know from our everyday life. As mentioned in the previous video, the photon is the force carrier of this force, and we will see that explicitly in the Feynman diagrams. Since photons also constitute to visible light, we will also discuss some interactions of light, as this is also part of QED. This theory is one of the most successful theories in physics. An example of the success of QED is that it has produced the most accurate prediction in all of physics, which we have been able to experimentally test. In particular, I'm talking about the anomalous magnetic dipole moment of the electron, which has been measured to an accuracy of 1 part in a billion, and this perfectly matches with theory. One of the most important discoveries which led us to the theory of QED was the discovery of the Dirac equation in 1928. This was the first relativistic quantum equation, and we can write this equation as I partial d slashed minus m, and then all that times psi is equal to 0. Let us break down this equation. Starting from the left, we have the imaginary number I, which we find in most quantum equations. Next we have this partial d with a slash. The slash notation was invented by Feynman to make the notation more sleek. What you need to know about this is that it contains spin information. One can roughly say that it takes care of the orientation of the particle as it moves in space. The next term is simply the mass m of the particle which we consider. Then we have psi, which is the wave function of the particle, and it contains information about the position and time coordinate of the particle. This equation became the foundation of QED, as it is valid for fermions or spin-half particles. And as we learned in the previous video, the electromagnetic force is felt by all fermions except neutrinos. It turns out that the Dirac equation is almost what we need to construct QED. An interesting result is that the Dirac equation predicts antiparticles, something which is explicitly shown in the Lagrangian of QED. So without further ado, let's write down this main equation of quantum electrodynamics. The Lagrangian is equal to psi bar in parenthesis I slash d minus m in a parenthesis psi minus 1/4 times the field strength tensor squared. The first thing we note is that indeed the first term looks very similar to the Dirac equation. The first difference is that we have psi bar on the left. This is the wave function of antimatter, like the positron. And likewise, psi is still the wave function of the usual matter. In the parenthesis, we again have this imaginary number I, but we have a slight modification as we now have slashed capital D, but otherwise this term looks just like the Dirac equation, where again m is the mass. Now we also have a new kinetic term with the electromagnetic field tensors F mu nu. Tensors are matrix objects, and in this case it is the tensor with all the information about the electric and magnetic fields. This term actually contains all of Maxwell's equations. If you want to see how you can derive them from this term, let me know, but it's rather mathematical. Now let's go back to the slashed capital D. It's called the gauge covariant derivative. This is related to the fact that QED is a gauge theory. We can expand this term as capital D slashed is equal to partial D slashed plus I e gamma mu a mu. We see that the first term is the same as what we had in the Dirac equation, but now we have another term. This term contains the charge of the fermions which interact with the gauge field A mu. This gauge field is the electromagnetic field or photon field. Thus this term is exactly what gives us the Feynman rule for the vertex in QED. The gamma mu, roughly speaking, just contains spin information of the interacting fermions. Again, usually we consider electrons. Now that we have figured out the Feynman rules, let us get to the Feynman diagrams of QED. These diagrams are a bit more complicated than the toy model we considered in a previous video. Please check out that video to get more insights to the basics of Feynman diagrams. Now in QED there is simply one vertex, and that is the one we just discovered on the previous slide. This vertex leads to a single diagram, and all of QED is constructed from this single diagram. That's pretty crazy to think that all of electromagnetism is just one simple diagram. We can interpret this fundamental diagram in different ways just by turning it around. Remember, we consider time going from left to right. The fundamental diagram can, for example, represent the annihilation of matter and antimatter into a photon. We can also turn the diagram 90 degrees, and the diagram can represent absorption or emission of a photon. This is what happens, for example, in an atom, when you excite electrons and then they can emit a photon. This is also how lasers work. We can also rotate the diagram 90 degrees more, and then we obtain a diagram where a photon decays into a pair of matter and antimatter. Thus we can already understand several fundamental processes by considering the fundamental vertex of QED. So what more can we do? Well, we can of course combine two of these vertices and create scattering diagrams. These diagrams allow us to discuss repulsion and attraction. Let us first start with repulsion. In our everyday life, it will often be something like electrons we consider. So let's make a diagram where two electrons repel each other. In this diagram we have two incoming and two outgoing electrons. It is also called Müller scattering. Because the electrons have the same charge, they will repel each other. This repulsion is mediated by the photon. The photon in this case is virtual, as it is acting as a force carrier and not like a real light. Now, in the quantum world, electrons are indistinguishable. Thus, if we have two electrons, we have no way of labeling them because they are identical. Because of that, there is an additional diagram which we must consider in our calculation of the repulsion of electrons. This diagram is basically the same, but the outgoing electrons are swapped because we can't distinguish between the two electrons. Now all you would need to do to get a number which we could test in an experiment is to compute both these Feynman diagrams using the relevant Feynman rules. Next we can consider attraction. This is what happens when two particles with opposite charge interact with each other. This process is called Barbour scattering, and a simple example would be where an electron and a positron attract each other. In this case we can draw a diagram very similar to the repulsion example, but now we have an incoming and outgoing positron and electron, and again these two particles interact via a virtual photon. Now note that the fermion lines go the opposite way for the positron because it is antimatter. Unlike the case with the two electrons, we can distinguish between the positron and the electron, so there is no cross diagram. But because we have a pair of matter and antimatter, we get another diagram which we must consider. This is the annihilation diagram when the electron and positron annihilate into a photon and form again from the photon. So again we would have to consider both diagrams to compute this interaction. As promised, we will also look into light interaction, because this is also part of QED. If we combine two vertices in a slightly different way, we can make the so-called Compton scattering diagrams. In this process we start with a photon and a fermion, and again we will choose an electron for simplicity. This is a real photon which interacts with the electron. The new thing here is that the mediator in this case is not a photon but a fermion, and again we consider an electron. Eventually we get an outgoing electron and a photon. This process also has two diagrams. One is in the form of an annihilation diagram and the other is the usual interaction diagram, which we have seen for all of the processes so far. But note that the incoming photon turns into an electron. Likewise, the incoming electron then turns into a photon. This is a bit different. These processes are one of the primary ways in which light interacts with matter. Just as a bonus, there is actually also a special higher order diagram called a box diagram, where two photons interact with each other via a loop. Note this is not allowed at tree level, but only at loop level, and therefore it is a more exotic process. This video only covers some of the most essential processes of QED and the underlying theory behind it. We have seen that we can understand the electromagnetic force from a rather simple Lagrangian, and we can study the processes of QED by making diagrams based on a single type of vertex. There is still much deeper math to understand and many other processes which we could be interested in. You can combine fundamental vertices in an endless amount of ways, giving you more complicated diagrams. I think this video covers some of the most important processes, but if you think I missed an important process, let me know in the comment section with any other feedback or questions. As always, I hope you liked this video. If you did, please like and subscribe. If you want to support the channel, check out the link below. This will help me a lot in order to keep the channel going. See you in the next video. Stay tuned.